My name is Andrew Pittman, and this is a spatial analytic web application I've developed with University of Wisconsin's GIS Web Map Programming Master's Track, specifically Capstone Project 1. This application was designed specifically to dive into the potential relationship between well nitrate data and normalized cancer rates within the state of Wisconsin. This application has multiple different ways that the user can interact and focus and deep dive into analytic situations and scenarios. Mapbox.gl includes zooming, panning, as well as tilt and rotate options. There's also a full screen capability as well. I've included a splash screen that dives into some background on the project, as well as some explanation in terms of the aggregation and regression options, methods that were chosen to calculate the different data layers in this project. Different contact information is provided as well. In the upper right, we have an analytic toolbar for toggling layers on and off, providing different inputs for the aggregation layers that feed the spatial regression layer. An export button for the spatial regression layer should further analysis be desired, as well as legends that are appropriate for whatever layer the user is currently viewing. This application utilizes Mapbox.gl, React, Turf.js, Material UI, and a few others. It's a completely client-side architecture. That decision was made to emphasize and increase user experience, as there's no backend data calls or database interactions needed to perform this analysis. On application load, two layers are shown to the user, both the point data within the well nitrate data layer, as well as the polygon layer representing census cancer data. So at a high level, these are shown to the user quickly. It's hoped that the user is able to identify trends quickly before the spatial regression layer is shown. This is actually calculated as well, but hidden from the user on load. In the case of the two raw data layers loaded for the user initially, the well nitrate data actually has two visual affordances for quick trend isolation. Smaller blue circles indicate lower nitrate values, and larger red circles indicate higher nitrate values. Cancer rates are shown in the polygons via a single visual affordance, the color value. So rates should be trends in the data and correlations should be somewhat available to the user right off the bat. For further analysis, the spatial regression layer is actually available and pre-calculated based on two inputs. So this spatial regression layer is being calculated via the inverse distance weighting aggregation method. So that's being applied to both these raw input layers. And then once those two output polygon layers are calculated, in this case, hexagon polygons are calculated, the regression is calculated after the fact and shown to the user via this toggle. These values, this K of 3 value and 9 kilometer hexagon diameter size value are notional. They're just simple user start values. They're able to interact with these should they desire for further analysis. So the user is able to toggle this on after a few seconds of application, after the application loads. This layer shows primarily standardized residual values for different hexagons within the state of Wisconsin. As emphasized by this legend here, we have low standardized residuals represented by small green hexagons. This shows a low value of 0.08. In the case of higher hexagon values, or like higher in terms of height extrusions, for yellow hexagons, we have higher negative standardized residual, which indicates that the predicted cancer rate is higher than the actual cancer rate. The opposite is true in the case of the teal polygons. The predicted cancer rate is much lower than the actual cancer rate in this case. The absolute value of this was chosen to represent the height of the polygon, as both high negative standardized residuals and high positive standardized residuals both indicate a poor fit for the regression equation in the layer. The user's quickly able to utilize multiple visual affordances to identify trends here. They're able to recalculate these values as needed and see if the trends still hold true. Generally, in using this tool, I found that the trends do hold true regardless of choice for these input parameters. The user is able to toggle and enter inputs as well. These inputs are being constrained so that the user is not able to crash the application with arbitrary inputs or text values. If the user would like, they can export this data as GeoJSON. The file is tagged with the K value and the size value as appropriate. And all data used to calculate as well as output data for the regression is shown within this feature layer, as shown here. This application is open sourced and available on GitHub now, and it is live at pitman.dev/spatial analysis. Different use cases are identified on this GitHub page for further analysis and deep dives, should that be required. Further development is indicated here as well. As an output from this, in terms of what can be learned, this spatial regression layer shows both in visual form the standardized residual, but also within the tooltip the R-squared value. The R-squared value is a goodness of fit indicator across this entire layer. Generally, as shown, the R-squared value indicates a good fit as it's closer to 100% and poor fit as it's closer to 0%. I've done numerous calculations with this tool. This is actually the highest R-squared value that can be achieved with this tool. And this indicates that it is very unlikely that the independent variable is able to accurately predict the dependent variable. So the independent variable being the nitrate values or rates, and the dependent variable being the normalized cancer rates. Perhaps more research is needed, or other independent variables or more complex fit or regression calculation is needed. But in this instance, I'd have to say that nitrate values do a poor job of indicating cancer rates.